The first thing that I want to say is that this video is optional. You don't have to watch it. I'm going to show the calculus-based derivations of the rotational inertia formulas. You don't need to know it for the AP Physics 1 exam. If you are taking the AP Physics C exam, or you plan to, or you know that you'll be taking calculus-based physics in college, this would be a helpful video for you to watch. Also, if you're taking calculus and you find yourself constantly wondering, what do you actually use this for? They say that this gets used in, you have to know this if you're going into science, but like, where would you use it? I'm going to show you guys some example problems right here that show where calculus actually comes up beyond just a calculus class. So I find this to be interesting. This was one of my favorite things that I ever learned in physics, and I thought it was kind of a fun activity. I don't know if fun's the right word. Fun the way that Sudokus are fun. So that's why I'm sharing this video. But once again, don't feel like you have to watch this video. It's not going to come up on the video quiz, and it's not going to come up anywhere on any of the tests. So let's start this off. The definition in calculus for the rotational inertia of an object is I equals the integral of r squared dm, where dm represents all of the little masses that are rotating about the center of mass, and the little r represents the distance for each one of those masses. So the first thing that I'm going to do is I'm going to be trying to get this into a single variable to take the derivative or the integral of, so that I don't have to do any kind of weird partial integration type steps. So going through the steps now, the first thing that I'm going to do is I'm going to define the linear density of the rod. And the linear density is the length of the rod, which I'm going to use capital R to represent the length of the rod, where I'm using lowercase r to represent the distance for each center of mass to each mass to the center of rotation. So the linear density again is rho equals the total length r divided by the mass. I can also, though, define a small segment. Let's call an impossibly thin piece a slice of this rod, the dm of this rod. I'm going to say that the density of them is going to have a similar formula. It's going to be the length of that thing, dr, because it's just, if we like zoomed in on there, it would have an infinitesimally thin slice, dr, and that would have a mass of dm. So I can combine these two things together now to solve in terms of dm. I can say rho times dm equals dr. Then I can pull this rho in down and plug it in. So I can say capital R over capital M times dm equals dr. And then my last step, because I want to get dm by itself, is I can say dm is equal to m over r times dr. I just multiply both sides by the reciprocal. Now I can plug that into my rotational inertia formula. And if I'm doing it for the rod, I'm going to integrate it with respect to the total length of the rod. So I'm going to go from 0 to r of r squared times m over capital R dr. Now, capital M and capital R are both constants in this problem, meaning that if I was trying to find the rotational inertia of a real rod, I would be able to measure right at the beginning the mass and the length of the rod without any problems. I can't plug in all of the infinitesimal numbers of little r's for each dm, and I can't measure each dr. So those things are still variables, but since m and r are constants, I can pull them out front. And then I'm just going to integrate r squared dr. So this is an easy thing to integrate. The calculus step here is pretty simple. Power rule r cubed over 3. Still have those constants, and I still have to go from 0 to r. So then this is m over r times r to the third over 3 minus 0 to the third over 3. And this simplifies down to the rotational inertia for this rod is going to be equal to 1/3. Let's see, that all cancels. This r on the bottom cancels one of those r, so it becomes r squared. It becomes mr squared, 1/3 mr squared. So, and that matches what was on the table that I shared with you guys in the earlier video. So that's the rotational inertia of a rod. Let's do the rotational inertia of a ring. This one's pretty ugly. I like it. The density of the rod, or of the ring, is going to be the total circumference. That's 2 pi r all over the mass of the whole thing. So basically, I'm just saying, in a similar way that I found the linear density here, I'm taking the total length of the circumference of this very, very thin ring, dividing by mass. And if I chop that into pieces, I could then find the mass of any of those pieces by just knowing how long it is and then multiplying it by the density. I can also write the density of my small dm chunk. This little dm chunk is going to have a angular width of d theta. So that would be d theta times still big R all over dm. So basically, I'm just taking the arc length times R and dividing by the impossibly small mass in the same way that I found the total arc length of the whole circle times the radius times the mass of the whole circle. So this is just, they both equal the density. This is just the density using a very small chunk, and this is the density using the whole thing. So from there, I can do similar steps to what I did earlier, saying that dm or rho dm equals d theta r. And then I can plug in this density formula here in place of rho. So I can say 2 pi r all over m times dm equals d theta r. And let's see, do I like the way that this is going? I think I do. Yeah. So I'm just going to go, let's see, one more step. I think my radii cancel right here because there's an r on each side. And then I can multiply each side by the reciprocal of 2 pi over m. So I get dm equals m over 2 pi times d theta. So I'm going to plug that back into my rotational inertia formula. I equals the integral of r squared dm. But what's interesting here is this r value is actually constant for a ring. All of the points are always going to be the exact same distance away. So I can rewrite this as capital R squared. And I'm going to put in m over 2 pi d theta into my equation here, which means I'm going to actually integrate this with respect to theta, because theta is the thing that's going to be changing here instead of r. So I can pull out my constants again. All of these things are constants in the problem. The radius is something we could measure ahead of time. The mass, the total mass I can measure ahead of time. And obviously 2 pi is a constant. So I'm going to have mr squared out front over 2 pi. And I'm going to integrate this from 0 to 2 pi. That will account for every single chunk all the way around the circle, because I'm doing the full 2 pi radians. And then that's going to be integrating with respect to d theta. So this is a very easy integral to do. It's just going to be theta from 0 to 2 pi times my constants, mr squared over 2 pi. Then this would be mr squared over 2 pi times 2 pi minus 0. Obviously 0 we don't really care about. That's 2 pi on the top, 2 pi on the bottom. That also cancels. And we get the rotational inertia of a ring is actually just equal to mr squared. So that was a really long time path to take just to get a very simple result. But we're actually going to use that result in our next one. Because with the disk now, I can't just do individual pieces because the pieces exist in all different locations. And there's more R's at the like small, what am I trying to say? If we were imagining all of these as infinitely small points, there's still more points around the outside of the edge than there are near the middle. So I can't just say I have one point and then another point a little bit further out, another point further out, because I wouldn't be accounting for all of the points that exist at the outside compared to the inside. So instead, I'm going to use, I'm going to treat my disk as being an infinite number of rings that are like infinitely thin. So each one of those rings is going to have distance of r from the center and a thickness of dr. So from here, I can do my density work again. This time for my density work, I'm going to say that my density of this flat disk is just going to be the area of the entire disk. That's pi r squared all over the mass of that whole disk. The density of my rings, though, I'm going to still need to find the area of my ring. So the area is going to be the distance, the circumference, that is, 2 pi r, then times dr. That way I'm accounting for the entire distance around. So that's 1 dimension times the thickness, that's 2 dimensions. So I basically have 2 dimensions in my original density, and I have 2 dimensions here. The radius, or the circumference, times the thickness. That's all going to be over dm. So that accounts for every single piece with those r's and those drs. Oh, oops, I should need to fix this r in my first density. That needs to be capital R because that's the radius of the entire disk. So I'm going to go through here. Dm, rho dm equals 2 pi r dr. I can plug in my rho there. So that's pi r squared over m dm equals 2 pi r dr. Let's see, my pi's cancel, so let's just get rid of those right now. And I can multiply both sides by m over r squared. So I get dm equals 2r times m dr all over r squared. Okay, I'm not actually satisfied with how I got separated my variables out. So let's get 2m over r squared times r dr. That's a little bit better because now I have all the constants collected. So I can use my rotational inertia formula again. I equals, I'm going to be integrating this for every single ring that could exist. So from the first ring that exists at a distance of effectively 0 from my center of rotation, and then every r ring moving outwards all the way out to the furthest out point. And that's going to be r squared times dm. But I know that dm is this giant mess here, 2m over r squared r dr. So I can pull all the constants out front. That's going to be 2m over r squared. And then I'm going to integrate with respect to I have 2 r's there, so that's r squared dr. All right, power rule. Once again, I'm not liking what's happening here. Hold on one sec. Yeah, this should be r squared. This should be r to the third. Yeah, there we go. Okay, should be r to the third right there. Because we had an r squared here and an r there. So when I integrate that, it's going to be r to the fourth over 4 from 0 to r times 2 pi over r squared, which is equal to 2. Oh, there's no pi there, is there? 2m. There it is. 2m. 2m. 2m over r squared times r to the fourth over 4 minus 0. Let's see. The 4 and the 2 there simplify to 1/2. Can pull the m out, and I have an r to the fourth and an r squared, so that becomes r squared. That's m of a disk, or rotational inertia of a disk. So there's the first 3 rotational inertia derivations that you would do in any calculus-based physics course. The next one to do is a sphere. So if you are interested in trying to do some more of these on your own, I'll give you the hint that if you're going to do a sphere, there's one of 2 ways to do it. You could either treat it as an infinite series of a stack of disks. So if we're rotating along this axis here, we just do a stack of disks that descend down that way. Or you could do an infinite number of cylinders. And cylinders would be very similar to doing rings. So either way you want to do that, if you want to try and attempt those, and let me know if you get stuck, if you want any help. This is the video on rotational inertia derivations. I hope it was helpful and not a giant mess. Thanks. Bye.